Sam's asked me to ring the bell at 18 minutes. So over to you, Sam.
All right. All right, welcome everyone. I'm excited to talk to you today about a project we've been working on at Deakin Rural Health and Centre for Australian Research and Access on calculating distance and time calculations at a very efficient scale. So I'm Sam Quincy. I'm an Associate Research Fellow at the Centre for Australian Research into Access. Just like to acknowledge some of my other teammates involved in this. So Marcus Blake, who's in the room here today, is our Technical Manager. And then Professor Neil Coffey and Professor Vincent Versace are both big drivers of the project and everything that we do at CARA as well. So the Centre for Australian Research into Access is a collaborative research initiative led by Deakin Rural Health. We look at access-related research for particularly health, but also education and other subject matter as well. So the project I'm going to talk to you about today came about because of traditionally a poor resolution of health data in Australia. Often it's given out at an aggregate level already, which does make it harder to define, obviously, at a smaller level from there. So we have come up with a solution to do everything, calculations of time, distance, and any other impedance that can be added to network data to calculate things at the dwelling level. So the project itself has been split up into two parts. So the first thing that we needed to do was create a more effective residential dwelling register for Australia. We do have GNAF and the address register through the Australian Bureau of Statistics, although it's not an open data set, which does have some missing coverage throughout Australia, and particularly in the remote areas, which is such a big focus of what we do at CARA. So that is probably a talk of its own, and I won't go into any detail on how we came about developing that today. But then with that data set, we then have created a method for calculating from these dwelling points to a variety of services, both time and distance. So we've built a Python module and then used Jupyter Notebooks to run all of the different code, and the main calculation that we do is nearest calculations. So this can be to the nearest or however many nearest a user wants to specify. So from each origin to a number of nearest destinations for a particular data set. And then we can use that, because it's at the dwelling level, we can then spatially aggregate this to any geometry that we want to. These are the two that I'll be focusing on today, but within our Python modules, we also have methods for calculating destination catchments, so within a specified time or distance, and then also direct origin to destination matrices if you need to be really specific about the origin and destination routes. So our library is built on top of Geopandas and Pandas for our tabular data, and then Pandana is for our network creation analysis. Has anyone here used Pandana at all before or familiar with it? Yeah. So it's very effective and very quick at calculating the network analysis component of our project here. It uses contraction hierarchies on top of a Dijkstra algorithm, and is, as you'll see with some of the times that I show you a bit later, very, very quick and effective at doing this. So we built a class called the network calculator class, which upon instantiation requires a series of data sets to be input into it. So the first one I'll mention is the origins. So this is our just over 10.5 million points that we created for our dwelling register. And this is built on top of mesh block counts from the Australian Bureau of Statistics, GNAF for the original geometries, but then those geometries are pulled to Overture map building footprint centroids to give a better representation of where the physical location of each of those dwellings are. Destination data sets, we've done anything from one destination through to 284,000 destinations for a single calculation. And these can be derived from, we've used things from Overture maps, so the places that you can download from there can be separated into different services, as well as other data sets from the Australian National Health Service Directory, among others. For the network analysis component, we need a nodes and an edges data frame, or data set. So we've used, again, Overture maps. It's, for anyone who's not familiar with that, it's very, like you can download open source data for any bounding box that you want to specify. So we've been able to get that for all of Australia. But then we've also used some commercial data sets, as these give us a bit more, they give us some time calculations that we can do as well, which is lacking in the Overture data at the moment. Quickly mention the islands. These will come up a bit later as to why we have an islands data set in there, but it just helps us to maintain realistic calculations throughout, especially somewhere like Australia where we have lots of little islands dotted around our mainland. So the total calculation splits up into 3 components. Both the origins and the destination points need to be connected to points within our network, and then Pandana is used for the main component of the entire calculation. I'll move on to the different components of how we do this. So connecting to the network, this applies to both the origins and the destinations, and there's a few different methods that we've used for this with different advantages to each method. So the quickest and easiest is to simply connect a straight line distance to the nearest node. This does have some problems as far as it does create unrealistic connections to the network. So we have, you can see somewhat in the middle of the screen there, we have some of our origins jumping over a road and going to a cul-de-sac, which obviously in the real world is not realistic. So something that is a little bit better for that is to connect to the nearest edge using Geopandas methods, and then from that edge we can then calculate to both nodes at either end of that edge and then select the shorter of those 2 distances. Still has its issues, but we do believe that overall this is a better way of connecting to the network, but is a little bit more computationally time consuming than just connecting to the nodes. So as part of all of our connections to the network though, we do like to use these islands that I mentioned earlier to restrict some of our connections. So this removes the instances where, as you can see on that smaller island on the right there, we are not allowing those origins to connect to a network on another island, despite the fact that these origins do not have a network of their own on the same island. Basically, these just become disconnected for all calculations, but it's to maintain that realisticness throughout. Even now, some of our standard connections, though, do have some errors in them, and these are things that we need to sort out in the future. These are obviously all on the same island. It's just that because of the river systems north of Sydney there, things can get a little bit thrown out of whack when their network doesn't have the coverage that it would ideally have. And then just one that we're experimenting a bit more with is to insert nodes within the network. We think this obviously creates the most realistic connection, but it is a lot more computationally heavy. And we do think it's worth implementing this maybe in rural areas a lot more. As you can see, there is quite a distance. This is a little subset of data that I've taken from near Coober Pedy in northern South Australia or central South Australia, where obviously where the nodes are is really important as to where those connections are made to the network. So we think this is a really good case of where, like maybe in the more remote areas, we do create these additional nodes and insert them, but otherwise we use the more computationally effective methods. Once our origins and destinations have been connected to the network, we can then start to instantiate a network object using Pandanas. Prior to this though, we do have the option to modify our network a little bit if we wanted to do something like simulate a road closure, or if we have a natural disaster that causes a lot of flooding or something like that and we want to take out whole chunks of the network. We can do this by clipping to an extent or a bounding box to restrict the network. This does improve the time of calculations as well if you need it to be more efficient that way. We can just remove one or more nodes, which will also remove edges that are corresponding, and then also just the edges themselves. So there's a lot of versatility in how we can modify the network here. And then once we've done all that, we can then instantiate our object. So this is using the Pandana network object, and we just need to input a few bits of information about the node latitude and longitudes, the nodes that are either end of each of the edges in the edges network, and then we can insert a list of impedances. So Pandana will accept more than one for a single calculation. From there, we are just doing the part of the calculation in the orange box that you can see on the screen there. So the user will specify how many nearest destinations from each origin point that you'd like to calculate to. One thing I should note is that realistically in this calculation, we're not going from every origin, we're going from every network node, and then those origins just have a connection to that part of the network. But from that user specified number, we just do a few checks just to make sure that our number is less than the total number of destinations, so that we're not exceeding that unnecessarily. And then because of the way that Pandana calculates, and it doesn't know about those distances on either end, and as you can see in that image there, it could be a case of the longest network distance is not the longest overall distance. We actually just modify that number of calculations just so that we can assess that at the end of everything and actually determine which is the nearest calculation there. So I'm calling that the total distance limitation. And again, in urban areas where everything's really close, it doesn't maybe make a large impact, but where all of these three origins go to the same node, it is important to know that all of these three calculations are going to come out exactly the same in the Pandana component of the calculation. So we do need to make those additional calculations to determine which one overall of these three would be the nearest. Finally, I just want to mention that there is another issue that we're calling the multiple impedance limitation. It's an issue within Pandana that I've found a workaround for. I don't necessarily know how to fix it within the Pandana code. I'll mention more about that after the calculation component though, when it becomes a bit clearer as to what that is. So once our object's instantiated within Pandanas, we are then starting to perform all of our calculations. So the first thing that we need to do is set the destinations within the network graph itself. And something we've done to maintain a lot more control over how these calculations occur is that instead of inserting the destinations, just where they are in space, we're actually inserting them on top of the node that they have connected to. The reason for doing this is there is a mapping distance parameter within this setPOIs method that allows us to restrict how far the point that we're setting can look for the nearest node. The reason for doing this is that if we set a really low distance and we want to then modify the network and maybe we have a road closure right here, which in that bottom image shows that connection that we've made to the network cannot then just unrealistically jump to the next nearest node. And it allows us to say, hey, something here has actually become disconnected from the network for a particular reason. Once those have been set, we can then use the nearest POIs method to perform all these calculations. So this is done very quickly and effectively with Pandanas and outputs a table for each impedance with the however many number of nearest you've specified plus the corresponding destinations for each of those. Where connections aren't made, we have used the distance parameter within this method to set a distance of 1 million to really differentiate it from actual calculations, and it just helps us deal with them down the line. It should be noted that for each impedance, a separate calculation has to be done for each impedance. It doesn't do them all at once, unfortunately, and this can add to quite a bit of the overall calculation time as well. Once all the different impedances have been done, if there is more than one, we can then combine them using Geopandas methods to calculate them back into one data frame. So that multiple impedance limitation that I mentioned is just something within Pandana where for every additional impedance beyond 1, it seems to duplicate the output. So your first nearest will also be the second nearest, and therefore your actual second nearest is the third nearest. It's just something we're aware of, and we have worked out a workaround, but obviously going from 3 calculations to 6 is increasing that computational time overall, and it is something that we endeavour to look into a bit more in the future as to find a permanent solution to not have to duplicate all of these. For every different impedance, there'll be an additional duplication. So now that we have those 3 components of the entire calculation done, we can then combine all these to get our total distances. So obviously the Pandana is only concerned about the node to node distances, and we need to add on that origin to node and destination to node distances as well. So we connect our network results to the origins that we can use the node ID that was done in the first component to do that. And then for every nearest and impedance combination, so the nearest distance and then the second nearest distance and then the nearest time, second nearest time, if we were to use more than one impedance, a merge needs to be done for each one of those to get all of those different calculations. Once that's been done, we can then, once that's been done, this is why we do those additional calculations, because once we add on those 2 end values, you may find that the nearest is not actually the nearest. Therefore, we can sort those out and remove those additional ones that we've done once we actually know which is the shortest overall. So some of the times that are occurring throughout this calculation, so the instantiation takes on some of the testing that I've done are roughly 1:35. So this involves reading in the origins destinations, nodes, edges, islands, data frames, and just sorting out a few of the schema checks that need to be done during that instantiation. The network connections is definitely the most time consuming, but there is means to reduce the overall time that we want to do that we have for this. So because our origins data set is so large, it takes almost 20 minutes to do that on this particular one that I've used for the example here. So this is going from origins to our Overture Maps network here, and that is around just under 20 minutes to do that. Once this has been done once for the origins though, you don't need to do it for subsequent calculations. So for every other calculation, you're not doing that additional 20 minutes, saving a significant amount of time. Therefore, the destinations are only 2 minutes. This is on a data set of almost 8,000 points. And obviously the less destinations, the faster that is. Then the network creation, which is done with the Pandana instantiation, that's with 7 million edges and 3 million nodes. So the edges get quite large when you end up flipping parts of the network, so it ends up usually being just under double what the nodes are, but that allows us to obviously have multi-way within the network. And then calculating those nearest calculations, this is where the Pandana calculations are very effective, is only 1.5 minutes on one impedance. So for every additional impedance, that is going to add a certain amount of time. It doesn't necessarily double it for each one, but it's just that little bit more time when you have further impedances. And then to sum those totals, we just have the 2 minutes. So it's a half an hour calculation if you need to do those origins, but for every subsequent calculation, you save that 20 minutes of not having to connect the origins, allowing us to do this in under 10 minutes. So we have a fair bit of variance with this, and it depends on the machine that you're running it on as well. Anywhere from 6 minutes to 10 minutes is usually an average calculation time if we're not having to do those origins as well. And then I've just noted a few of the impacts for the time there. So obviously the size of all the data and the number of nodes, edges, and origins and destinations does affect that time. Whether the origin's already connected or not, the number of impedances, and then also number of destinations. So looking at some of our results here, this is an example of calculating from every origin point in Australia to every general practice in the 2021 dataset from the National Health Service Directory. This just shows just how vast the scale is of what we're doing. And then just showing that zoomed in level that this isn't just a surface, this is individual points on a map to do that. So then this allows us, we can do some temporal change and have a look at that. I know these two maps don't look the same, do look exactly the same. So yeah, once you actually do a bit of further analysis, you can see where those differences are occurring in time. This is a direct difference, so just subtracting one from the other. But if we look at the mean of all those differences and then look beyond one standard deviation, we can just get a feel for which ones are more impacted than others. And there are many other methods for assessing this sort of change as well. And then finally, I just want to talk on the fact that we can aggregate all of our different dwellings to any aggregation level that we want. So as I discussed at the start, we talked about how things are given out at the aggregated level. The fact that we can do this at the dwelling level means that we can have control over those aggregations. So they can be anything from statistical units, like local government areas or statistical area ones, or completely random geometry, well, not random geometries, but maybe not, like any sort of geometry like land cover or surface catchments can be done among many, many others. So this is a new class within our module called the Spatial Aggregator class. It basically takes in the results of the previous calculation that I've been talking about, any geometry unit that you want, and then a series of statistics. So we have a set of default statistics that we output with ours, but it also accepts any other NumPy statistics that can be inserted there. Thank you all for listening. If you have any questions, please let me know.
Questions?
Hi, thanks for that talk. I'm really interested in how, if you have other measures of access as well, so whether you just do distance or whether you're also looking at travel times and potentially travel times by different modes.
Yeah, so Obviously, the open source that we have is the Overture Maps data, but we do have a commercial data set from Precisely as well. Now, Precisely offers, I think it's 7 different time metrics. So you've got like AM peak, PM peak, night peak, average 7-day peak. So we have lots of different time calculations that we can use with that commercial data set as well, and it is something that we use quite often. And one that we're also thinking of looking into a lot more is cost. So it's just hard to quantify that, like what is the cost over a distance, but it's just an impedance that we've thought can be thrown in there. So yes, the answer is yes, we are using time as well.
And do you have anything for separating out car access versus non-car access, especially public transport?
Within like the Overture Maps data, it's obviously built on top of a lot of OSM data, so it's we can make it as effective as the attributes allow. If the attributes aren't there, then we can't take those sorts of routes out. But yes, we are building our networks with a lot of that in mind and trying to really be quite strict on what roads we allow and what we don't. But obviously there's being open source and contributed by the public, there's all sorts of variances that we have to allow for too. Yeah.
Thank you.
Any more questions? I've got a bit of a random question. If we're talking about time as a cost, is perhaps speed limit information available open source for a road network?
On the Overture Maps again that we've been using, you get some max speed, like so the posted speed limit, but you don't, like so the Precisely network that we use, they collaborate with TomTom and they get people's actual speed and travel data. This is why you can get those different AM peak, PM peak and average speed times. So that's why that commercial data set is a little bit better for us in that particular instance where we're trying to do time. But yeah, unfortunately the OSM and whatnot is generally just a posted speed limit and the coverage is quite poor as well. So there's a lot of interpolation of unknown speed limits along roads and so you have to factor in things like the surface of the road and whether it can, like, you know, if you're in a rural part, is it a dirt road, so can you do 100 k's an hour on it? That sort of thing as well. It's a lot harder, especially in remote Australia.
Australia suffers, and for such a large country that is really dependent on a road network, it suffers from having not having a road network that can be used for this type of work very easily at all. So the networks it has there's a data set from Geoscape, which is a wholly owned government organisation that creates commercial data sets, which is an aggregation of all the state road networks. And as an aggregation, it's a mess. In terms of half the roads in that data set are in New South Wales, so there's New South Wales maps every fire trail there is across New South Wales, while other states do have other standards. So there's a standards issue in Australia. The OpenStreetMaps and Overture dataset model is pretty equivalent to the commercial datasets, except where it isn't. There's still about 50% nulls in terms of posted speed limits in there. So when you come to try and do this for the whole of Australia, it's a problem. We have to assume a certain national speed limits on roads that we don't have any information on. The beauty of the Precisely data set is that they've used floating car data, which is people with their iPhone or their phones on collecting information, and they've got information for most of the roads across Australia. So that's the advantage there.
Oh, we've got a question.
Thanks. Really two questions, if I may, but one was, did you consider deploying this on something like PG routing or something that would allow you to just operationalize it? Maybe you just say that Pandana was my poison and like it and it's fine, right? I'm just wondering whether you have considered any other more optimized routing engines.
Not yet. This is kind of, this has just been what we've been developing for the last 18 months, and this is kind of it coming to a head now. So we haven't looked too much into the future yet, but it's certainly something.
Because you're using Dijkstra still there, right?
Within Pandana,
so
yes.
You can certainly go A-star at least, and you'll speed up infinitely, because you have everything for the heuristic. You have georeferenced nodes, so you would speed up hugely with A-star. The second question I had was, did you consider all of your findings about the gaps in the data for overture maps or whatever, when you have missing attributes, to put that up to map roulette or in some way actually informing the community what's missing? That would be golden information. You know, it would be great to know where the gaps are because someone has actually used the data for routing, whatever, not just for cartographic purposes, so that you can fill it in.
Yeah, no, it's a very good comment. Like, we definitely need to. It's still something we're fairly new to as overture maps, so we're still kind of exploring that data as well a lot more. But yeah, certainly it's something that we can do in the future.
Okay, we need to finish up there. Please join me to thank Sam.